So the other thing I want to talk about then is just the review what we talked about at the start of last compressive lecture, hyperspectral imaging strategies and where compressive sensing fits in. So again, remember, and when we talked about optical microscopies, a silicon camera is gray. It doesn't see color. We add these Bayer patterns. So the smiley face, to get it into color, we basically have to put color filters over every pixel. And instead of seeing all the subtleties, these colors are blocked into only 3 channels. We could again do the filter wheel version of hyperspectral. And in that case, we're building up each spatial layer, X and Y, by different lambdas. So we can go from the ultraviolet to the blue, to the cyan, to the greens, to the yellow, to the orange, and so on. So that's one strategy. But the more color channels you want, the more filters you're going to have on your wheel. We can also take and put a spectrometer, and then we can do it by whisk broom. So that again, we can raster scan the different pixels. And that's what this looks like when you're creating the cube. Again, what's really popular in a lot of labs is the push broom, where you take a 2D array and then you space it out between Y and lambda, and then you scan a slit in X. So what I showed you before is replacing the single pixel detector with a spectrometer, and that gives us 1,000 different single pixel cameras. And so what that looks like is the same pattern at every spectral channel. And you basically take these measurements, and then you change the pattern to a different measurement, and then basically, for every pattern on the DMD, you get a unique mixing spectrum, and then you plug it in and solve for those 1,000 different single pixel camera images. What if we spatially, spectrally compressed everything? What if we had the hyperspectral projector on the front, and instead of a grayscale camera on the back, what if we had another DMD and a single detector? Or what if we had on the back a spatial DMD, then we collimate the light, and then we have a spectral DMD? Then you would have this sort of even more random looking mixture of space and spectral information from your system. But instead of going to a line detector, it would all be squeezed down to a single. You could think about, when you're talking about spatial spectral compression, is you're talking about 3D CS, right? You're talking about X, T, Y, and lambda. And another thing you think about is X, Y, and time. Because you could ask the question also, what happens if the scene is changing while the pattern is changing, right? Is that bad or is that good? Mathematically, we actually know it's good. You know, we'll get back to why that is in a second. But when we first tried it, it's bad. We have an old-time metronome that swings like a pendulum, and it's swinging in front of this target. And if we try to go fast and catch the metronome, we can, but we can't read it. And if we slow down, the metronome's motion is so fast, it's like the beginning of class when we talked about that daguerreotype. And the idea that, you know, if you integrate too long, you won't see that thing. What we figured out is you could actually do this, but there's a trick. But the cool thing is when you do this, you get 60-to-1 compression or 100-to-1 compression or 200-to-1 compression. When I was talking about regular single pixel camera imaging, you get instead 10-to-1 compression or 20-to-1 compression at best. So why is it the compression keeps going up and the quality is the same even though we're solving a harder problem? And the answer is So for 2D CS, x and y, the sparseness goes as the square root of the number of pixels. In 3D CS, it goes as the cube root. So that if I go from an image that is a megapixel by a megapixel and 1,000 frames in video to 5,000, so 1,000 by 1,000 in x and y and 1,000 in time, to 5,000 in x, 5,000 in y, and 5,000 in time, my number of measurements only go up by 5. They don't go up by 125, which would be 5 cubed. The other thing is, we also needed to use something called optical flow. And this is a more complicated topic, but it's something even now electron microscopists need to use. And it's something that is what we saw on Monday from Emo Han's group and other people talking about, is how do you handle when your image is blurred during the capture. But again, we're not interpolating. It's really capturing these images. So these low-resolution images, for instance, of the hand, do not show the lines on the palm of the hand. There is no way through interpolation that that feature could be seen, but it is really captured in the compressive image. The dot in the center of the windmill cannot be resolved in the low-resolution feature, yet compressive sensing actually sees it. So now we return to this question. Again, this is 10 to 1 to 20 to 1 max compression, sometimes 50 to 1, but very rarely. This, in this case, again, it's just 1,000 spectral cameras, so it's not actually doing any compression in spectrum, so it's the same as this solution. When you go to video, or when you go to spatial-spectral, we'll go as the cube root of n. So then we're going to ask the question, what about 4D data? What if I wanted to capture x, y, t, and lambda? That should go as the fourth root of n in terms of the number of measurements I need to keep the same quality. And again, if you want to visualize this in terms of the equation, so when you talk about 4D information, in 3D information, it goes from a pixel to a voxel. And I didn't choose this term, the medical industry did, but when you go from a voxel to time, you go to a dynamic voxel, or what they call a doxel. So it's dynamic voxel. So let's look at our spatial sparsity. Again, compressive imaging in the sparseness of this image can be thought of as a transform, or it can be thought of as finding the edges and then filling in the colors of the regions after you found the edges. And so this is the total variation sparseness of this image. Mathematically, again, you're trying to minimize the first derivative here in x and y. Temporal sparsity. Why does temporal sparsity work here and for our video? The reason it works is this is not a 2D image. I used to cycle and be in shape a long time ago. I'm not anymore. But is there anything wrong you see with this image of cyclists? Look at the wheel spokes. They're not straight. Why aren't they straight? No, in fact, the trick is it's only a 1D camera. It is only taking an image here and it's flipping the shutter in time. And then it's assembling it in 2D. This is the line camera. And so these poor guys raced 200 kilometers and one guy lost by a couple centimeters. But because this looks like a regular image, it is sparse like a regular image. So again, we just look for the derivative in time. Because we do a lot of visible imaging work in my lab, both in microscopy and elsewhere, when you look at visible spectrum, you don't really want to try to find an edge based on the first derivative. You really want to find an edge in the second derivative. But that's sort of the trick of total variation minimization, finding where your signal is sparse and then assembling that. So what would this look like in practice? This is set up in lab. It's very complicated, so it's hard to get an idea what it looks like. But you come in, you change the spatial patterns, you come off, you collimate the light, you go through a grating or a prism, you encode the spectral patterns, and you focus it all down to a single detector. So again, you come off the spatial pattern, and this one spatial pattern is stretched into a vector, and you do a bunch of these spatial patterns. Then you do a spectral pattern. And again, the really interesting thing is when we first thought about this concept, we thought, okay, I'll hold the spatial pattern, and I'll do 20 or 30 spectral patterns, or 100 spectral patterns, and then I'll change the spatial pattern. Nope. You change the spatial and spectral patterns at the same time. You just willy-nilly say, I want this pattern here, and then that pattern there, and you don't take any more than that. That's it. And that gives you the 3D voxel. But again, we are sparse sampling these 3D voxels. And in fact, there are some of what you get. This is 128 by 128 spatial pixels by 64 spectral channels at 4 frames a second video, and all we took was 5,000 measurements a second off the detector. That's it, 5 kilohertz. So if you multiply 128 by 128 by 64 by 4.3, you get 4.5 million pixels in your 4D cube of data. That means we are getting a compression ratio of 900 to 1. And you can still read the Air Force target, and you can still see the color changes in this image. All to a single detector. That's how I visualize it. It's a really silly exercise, but I did 1 to 100 or 1 to 98 or something like that in a Word document. I changed the page numbers so it looks like this. This is one block of 5,000 data. It's this. This is all we measured. Right? Each of these little points here is one of the 5,000 measurements. This is all the data information we got back. That's a pretty ill-posed problem. Again, here's just some static images. And again, it's not only important to show the pictures, because this looks pretty correct compared to these two pictures. But when you look at the spectrum, they are not correct. You need this optical flow in there to get everything right. And again, you can even do in-member unmixing on this data as well. So you don't have to reconstruct the 4D cube. You could say, instead of wavelength, I would just want the chemical compositions on my other axis. And then one thing I didn't tell you was how long it takes to solve this ill-posed problem. Because this is how much you have, one of these blocks, and this is how much the equations have to go in and fill in. 3 to 4 hours. But you can take these mathematical L1 algorithms, like TV minimization or PDHG, and for this data, because it's grayscale and it's 64 by 64, this takes less than a second. You can replace it with a neural network, and you can speed it up. And so you can go from 27 seconds, because you take this number and multiply it by the number of spectral channels you want. And with neural networks, you go from this number to, from 15 milliseconds to 66 milliseconds. Neural networks are really nonlinear. The really interesting thing about them is they're also mathematical function impersonators. So it's impersonating an L1, but it's not an L1. And so there are times when you have to be very careful about that. We haven't applied it to the Doxel Imager just yet. But again, say you have your spectrometer and your 1,000 single pixel cameras. If you can reconstruct this fast, all these spectral channels, you don't have to worry about optical flow. Because you get this 320x speed up of having this on your spectrometer. And again, this is the PDHG versus our neural net. So it's a pretty good impersonator. It's not perfect, but it's pretty good.